Hello everyone. Now that I've gone over how to calculate limits of functions exactly using algebraic techniques and things like that, I can show you the basics of what a derivative is, starting at its formal definition. Whereas a function is written f of x, the derivative of a function is written f apostrophe x, called f prime x. And this equals the limit as delta x approaches 0 of delta f of x over delta x. For those who are not familiar with the symbol, delta simply means difference, also sometimes called change. You will often see the formal definition of the derivative also written in this way. Which is simply a longhand way of writing out the change in y over change in x, where h stands in place of change of x. Now that we have the formal definition of the derivative written out, we use this plus the properties of limits discussed in the last video to rigorously prove the derivatives of different specific functions. For example, the derivative of x squared is equal to this. And we can now work on this some more by multiplying x plus h squared which is x plus h times x plus h by the rules of algebra. This multiplied out form leaves us with x squared plus 2hx plus h squared. So when you subtract x squared from this full expanded form, you will notice that x squareds cancel out. And now you have 2hx plus h squared divided by h in your derivative definition. So the h in the denominator cancels out and removes 1h from the top, leaving you with 2x plus h, which, since the definition of derivative means that h approaches 0, means that all you are left with is 2x. In conclusion, the derivative of x squared is 2x. You can use similar procedures to prove that the derivative of x cubed is 3x squared, the derivative of x to the fourth power is 4x cubed, and so on. However, the algebra involved in the proof gets pretty tedious after a while, so it is often more convenient to memorize patterns. In this case, the pattern being that x raised to the nth power will always have a derivative of n times x raised to the power minus 1. A really useful derivative proof when it comes to the field of mechanics is the derivative of the sine and cosine functions. Because the sine and cosine functions are used to represent harmonic motion, like on a spring or pendulum. The first step in this proof requires that you remember an identity from trig class, which is that the sine of a plus b equals the sine of a times cosine of b plus the sine of b times the cosine of a. Therefore, we rewrite the sine of x plus h part. We can now use algebra to rewrite the derivative. By breaking this down into two separate fractions. We can now proceed to the next step, which is isolating the sine of x on the left fraction and isolating the cosine of x on the right-hand fraction. This means that you now have cosine of h minus 1 on the left-hand fraction. Although at this point, we would have to use special limits to continue the proof. The limit of cosine of x minus 1 divided by x equals 0. And the limit of sine of x divided by x equals 1. Therefore, we can now state that the derivative is sine of x times 0 plus the cosine of x times 1. This now uses simple algebra and arithmetic, so sine of x times 0 is 0, and cosine of x times 1 is cosine of x. Therefore, the derivative of sine of x is cosine of x. You can do the cosine derivation yourself, as the steps are basically identical to the sine proof, except that cosine of a plus b gives you a different formula, which is cosine of a times cosine of b minus sine of a times sine of b. But after using the identity, you would simplify using algebra and special limits, just like the sine proof. If you are curious and do not wish to do the derivation yourself, the derivative of cosine of x is negative 1 times sine of x. Another concept that works well for simple harmonic motion is the second derivative, which is simply the derivative of the derivative. The second derivative of sine and cosine, now that the first derivative has been proven, is very trivial, as the first derivative of sine of x is cosine of x, and it has just been shown that the first derivative of cosine of x is negative sine of x. Therefore, the second derivative of sine of x is negative sine of x. The second derivative of cosine x is very similarly easily proven. As the first derivative is negative sine of x, and the derivative of negative 1 times sine of x is negative 1 times cosine of x. Therefore, the second derivative of cosine of x is negative cosine of x. The neat behavior of assigning cosine functions with respect to their second derivative allows you to solve second-order differential equations with linear coefficients, i.e., an equation where you are asked to solve for the second derivative of a given function, or to solve for a function given a second derivative. In fact, second-order differential equations with linear coefficients is exactly what would describe the mathematics behind simple harmonic motion. And so the sine and cosine functions would be a perfect answer to those types of problems. In the next video, I will go over the Euler's number function, also called the exponential of x, how to prove its derivative, and how its relationship between itself and its derivative can be used to solve first-order differential equations, just like sine and cosine solve second-order differential equations.